How do you escape something when even light itself needs 100,000 years just to cross it? That's the basic problem you live inside right now. You're not floating in some vague, endless void. You are inside a specific object with a measured size, a structure, and a center that everything, including you, orbits around. Zoom out from Earth, past the planets, past the Kuiper Belt, past the outer comets. Keep going until the Sun is just one star among hundreds of billions. The shape you see is the Milky Way, a barred spiral galaxy. It is a flat disk of stars, gas and dust, with a bright bulge in the middle and a straight bar of stars cutting across that bulge. From the ends of that bar, spiral arms curve outward. The main disk is about 100,000 light-years across, and roughly 1,000 light-years thick where most of the stars sit. Those are not poetic numbers, those are direct measurements from astronomy. Now place yourself inside that structure. You are not in the centre, and you are not in one of the biggest spiral arms. The Sun sits around 27,000 light-years from the galactic centre, inside a smaller feature called the Orion Arm, basically a local spur between two larger arms. If you think of the big arms as the main lanes of a city, you live in a side lane, away from the brightest traffic. That position is not glamorous, but it is stable, and that is why the solar system has had time to exist and evolve. Here is the important point: you're not at rest. Right now you are moving around the centre of the galaxy at hundreds of kilometers per second along with the Sun and its planets. One full orbit, 1 year on this galactic scale, takes roughly 220 million of your normal years. During one of these orbits, continents drift, species appear and vanish, whole mountain ranges rise and erode away, all while your star quietly follows its path through the disk. At the centre of that path is not just a crowd of stars, there is a compact object with extreme mass, the supermassive black hole called Sagittarius, a star. It has about 4 million times the mass of the Sun squeezed into a very small region. We know it is there because we can track the orbits of stars close to the centre, and they whip around something invisible at high speed, following paths that only make sense if there is a huge mass hidden in the dark. Radio telescopes also pick up emission from hot gas falling into this central object. So you live in a system where everything is responding to that deep gravitational well, whether you notice it or not. So you are in a disk around 100,000 light-years wide, you are 27,000 light-years from the middle, and your star is locked into a long orbit around a 4 million solar mass black hole. That already sounds like a big rigid setup, but it becomes clearer when you look at how long light itself takes to cross your home. A light-year is the distance light travels in 1 year in a vacuum. When we say the Milky Way is about 100,000 light-years across, we are literally saying if a beam of light starts on one edge of the disk and heads in a straight line to the opposite edge, it takes around 100,000 years to get there. Think about a simple signal. Imagine a powerful light signal being sent from near one side of the galaxy to near the other. Even if you ignore all obstacles and assume perfect conditions, that signal will arrive tens of thousands of years later. No maintenance, no fuel, no breakdowns, just pure light, and still, the delay is far beyond any human timescale. Civilizations can rise, change, and disappear in less time than one cross-galaxy light trip. Now, space inside the galaxy is not a perfect vacuum. People often say space is empty, but in the Milky Way, that is only true in a casual sense. The disk is filled with what astronomers call the interstellar medium, a thin mix of gas and dust that lies between the stars. In many regions, there are just a few atoms per cubic centimetre, which sounds like nothing, but spread across light years, it is significant. In other places, there are giant molecular clouds, enormous cold regions made mainly of hydrogen molecules, mixed with other elements and dust. These clouds are the birthplaces of new stars and planets. We know this structure in detail because different kinds of telescopes see different parts of it. Radio telescopes map neutral hydrogen gas across the disk. Infrared telescopes see through dust that blocks visible light, revealing colder regions and embedded stars. Together, these observations build a picture of the Milky Way as a layered, clumpy disk, not a clean, empty arena. For a slow-moving star at normal speeds, this medium is not a big problem. For a fast-moving spacecraft, it is. Here is where the straightforward, unpleasant part comes in. Once you try to move a ship at a serious fraction of the speed of light, even tiny dust grains become dangerous. A grain of dust that would be harmless at low speeds becomes a high-energy impactor at very high speeds, hitting your hull with the energy of an explosive. Even single atoms at extreme relative speeds can damage materials over time, heating surfaces, knocking atoms out of place, and slowly grinding down your protection. So the empty galaxy turns into a thin but very real minefield as soon as you push your velocity. So put all of this together in simple terms. You live inside a disk about 100,000 light years wide. Your star sits well inside that disk, locked into an orbit that takes hundreds of millions of years, held by a central black hole with millions of solar masses. The whole disk is filled with a thin but persistent medium of gas and dust, which is mostly harmless at low speeds, but increasingly hostile as you go faster. Even light, which has no mass and never needs fuel, takes tens of thousands of years to cross the galaxy you call home. From that point of view, the phrase "leave the Milky Way" is not a casual phrase. It is a claim about beating all of those numbers at once: size, gravity, time, and environment. For any civilization built on matter like you, with engines that need fuel and machines that wear out, that is not just a hard problem, it is close to impossible on practical timescales. The next question then hits very directly when your best tools are rockets that struggle to get a few tens of kilometers per second. How do they stand any chance against a structure that needs thousands of times more speed just to cross, let alone to escape? How much speed can you really buy when every extra kilometer per second costs you more fuel than all the ones before it? That is the basic problem with rockets, and it is the first reason "let's just go faster" breaks the moment you zoom out from planets to a whole galaxy. Take the rocket equation in plain language. A rocket moves because it throws mass out the back. You want more final speed, you either throw that exhaust out faster or you throw out more of it. But the link between speed and fuel is not gentle. Ask for a little more final speed, and the fuel you need jumps a lot, not a little. Then that extra fuel makes the rocket heavier, so you need more fuel to push the extra fuel. It is a feedback loop that punishes every upgrade. That is why a launch rocket is almost all tank and almost no payload. The part you care about, the satellite or probe, is a small piece on top of a huge stack of propellant and engines. When it reaches orbit, almost all of that propellant is gone. A simple rule of thumb drops out of this: if you want twice the final speed, you need far more than twice the fuel. Try for 3 times, 4 times, 10 times the speed, and the propellant mass explodes. Very quickly, the ship becomes a thin shell wrapped around a giant fuel tank. On paper, you can keep adding stages, but in real life, structure, materials, and cost stop you long before the speeds you would need for anything like galactic travel. So what have we actually achieved? Voyager 1, the most distant human probe, is doing about 17 kilometers per second relative to the Sun. New Horizons, which flew past Pluto, is around 14 kilometers per second. The Parker Solar Probe, our speed champion, dives extremely close to the Sun and uses repeated flybys, and at its fastest has hit roughly 190 kilometers per second. That last number sounds huge, but look at the context. Parker is small, highly optimized, and uses the Sun's gravity as a slingshot. It carries no people, no big life support system, no heavy radiation shielding, and that speed is a brief peak near the Sun, not a long-term cruise for a loaded starship. Even if you somehow held 200 kilometers per second as a steady speed and flew straight across the Milky Way's disk, you would still be talking about hundreds of thousands of years to cross 100,000 light years. Now compare that to what the galaxy itself is doing. Stars like the Sun orbit the center at roughly 220 kilometers per second. Your fastest probe only briefly matches the speed your star has all the time as part of its orbit. And even that galactic orbital speed is not enough to escape. To actually leave the Milky Way from where the Sun is, you need a local escape speed around 500 to 600 kilometers per second. Line the scales up. Earth's escape speed is about 11 kilometers per second. That is already hard, but chemical rockets can do it by burning most of their mass as fuel. The Sun's orbital speed around the galaxy is about 220 kilometers per second. The local galactic escape speed is several hundred kilometers per second. Our best chemical rockets, even with clever gravity assists, barely touch those larger numbers, and only for tiny probes. For anything heavy and crude, chemical propulsion is finished long before you get close, so you naturally ask, what if we change the engine instead of just piling on more fuel? That is where advanced propulsion ideas show up. Ion drives throw out charged particles at very high exhaust speeds, which makes them very efficient. You get a lot of speed change per kilogram of propellant, but the thrust is extremely small. Over months and years, that gentle push adds up, and missions like Dawn have used it. But with the power levels we can realistically mount on a spacecraft, you stay far below any serious fraction of light speed. Nuclear thermal rockets go a step further. They use a nuclear reactor to heat a propellant instead of burning chemicals. That can roughly double the exhaust speed over a chemical engine, which helps, but it is still only a factor of 2. You do not suddenly jump from solar system scales to galaxy scales. Fusion-based designs, like the classic Project Daedalus concepts, aim higher. They imagine using fusion reactions to blast material out the back at a large fraction of light speed. In optimistic versions, if everything works and you accept a huge, complex vehicle with massive fuel tanks, you might get a ship up to a few percent of light speed, maybe 5 or 10%. Even then, look at what that actually buys you. 10% of the speed of light is about 30,000 kilometers per second. At that speed, to cross 100,000 light years, you are still in the ballpark of 1 million years of travel, and that is before you talk about accelerating up and braking at the other end. More conservative designs talk about 1% of light speed, which stretches the crossing time into tens of millions of years. The pattern is simple and brutal. Every time you push for more speed, the rocket equation punishes you. You improve the engine and the fuel mass, the power system, the waste heat, and the structural stress all grow together. Escaping Earth is barely within reach. Sending tiny probes to the outer solar system is barely within reach. Scale the same physics to the size of a galaxy, and the whole project stops looking like extreme engineering and starts looking like fantasy. This is the main takeaway here. The fuel problem does not stay small. It scales with you. The same basic law that makes it expensive to reach orbit makes it brutally expensive to chase high fractions of light speed, and essentially impossible for anything like us to reach the escape speeds a galaxy demands. The Milky Way is not a thing you drift out of, it is the system where rockets run into a wall of costs long before they run into the edge. And all of this still treats speed as only a question of fuel and hardware. It ignores the deeper rule written into the universe itself, the speed of light as a hard limit. As you start to push your dream starship anywhere near that limit, the energy cost does not just climb, it blows up. So when your already vicious rocket equation slams straight into that cosmic speed cap, what does that do to the dream of ever leaving a galaxy at all? Here is the hard truth most space fiction skips. The speed of light is not a goal you aim for. It is a wall you cannot punch through. Light moves at about 300,000 kilometers every second. Anything with mass, like a ship, can get closer and closer to that speed, but the energy price you pay for each step up gets worse and worse. The relationship is not linear. At low speeds, doubling your speed needs about 4 times the energy. As you get near the speed of light, each extra bit of speed needs a ridiculous jump in energy. The universe is basically saying, fine, you can go faster, but you will go broke long before you hit the limit. So when people talk casually about, we'll just go at half the speed of light, or we'll cruise at 90% of light speed, you have to ask a simple question. Where does the energy come from, and how do you move that energy around? Because kinetic energy, the energy of motion, goes up brutally fast with speed, and relativity makes that curve even steeper as you get close to the limit. You never actually reach the speed of light. You just pump in more and more energy for smaller and smaller gains in speed. Take a concrete example, no math symbols, just scale. Imagine a starship that is small by city standards but big by rocket standards, say 1,000 tons total, that is 1,000,000 kilograms. Now say you manage to push this thing to 10% of the speed of light. That is 30,000 kilometers every second. At that speed, the kinetic energy stored in that ship is gigantic, in the range of hundreds of billions of joules. That is already comparable to, or above, the total energy human civilization uses in a year. And that is just the energy in the moving ship itself, not the losses, not the energy wasted as heat, not the overhead of building and running the launch system. Now notice the nasty detail here. That is only 10% of light speed. If you decide you want 20%, you do not just double the energy, you need several times more. Go to 50% and the required energy absolutely explodes. Push toward 90% of light speed, and you're talking about energy budgets that start to rival the total output of stars over long periods. You're no longer doing engineering, you're trying to run a star as your personal engine. And you still have not talked about stopping. This is the next trap people ignore. Getting up to speed is only half the journey. If you want to actually arrive somewhere and not just blast through it at insane speed, you have to slow down again. Every bit of kinetic energy you painfully added to your ship, you have to get rid of at the other end. That means more fuel carried from the start or some huge external braking system waiting for you out there, which is even harder because someone has to build that first. So the total energy bill for a round trip is not reach 10% of light speed once. It is accelerate up, then decelerate, then if you ever want to come back, do the whole thing again in reverse. Every step multiplies the energy and infrastructure required. The 1,000-ton ship at 10% of light speed stops being a cool image and becomes a moving disaster-level energy stack that you somehow have to control safely for decades or centuries. Then there is the apparent loophole people like to bring up, relativity itself. Special relativity says that as you move close to the speed of light, time for you slows down compared to the outside universe. That means, in principle, if you ride a ship at 90% of light speed, a very long trip can feel much shorter to you on board. Maybe the journey that takes tens of thousands of years from an outside point of view feels like a few hundred years on the ship. That sounds like a cheat code. Here is the catch. It only helps the travelers, not the civilization that launched them. Back home, normal time still passes. If your ship spends 1,000 years of external time cruising between stars or across a chunk of the galaxy, that is 1,000 years for your home world. Languages shift, cultures collapse and rebuild. Maybe your species even evolves further. When you arrive, whatever sent you is gone or unrecognizable. From their point of view, you did not go on a trip, you left their history. So even if you had the god-tier engineering to build a ship that safely handles these speeds, even if you had the energy to push a massive hull to a large fraction of light speed and then slow it down, you have not solved the basic problem for a society. You've created a one-way, one history, one timeline journey. The people who launch are not the people who arrive. The culture that arrives is not the one that left. From the point of view of a species trying to leave the galaxy together, relativistic travel is not a solution. It is a way to cut your own story into disconnected pieces. Now connect this straight back to the Milky Way's scale. From where you sit, light itself needs more than 25,000 years just to get to the galactic center. To go from one edge of the disk to the opposite edge takes around 100,000 years at light speed. So ask yourself, what does 10% of light speed mean on that map? It means journey times of hundreds of thousands to 1,000,000 years. Even at 30, 40, 50% of light speed, you're talking about tens of thousands of years to cross major parts of the galaxy. At that point, the speed of light is not a nice high target you aim for with the better engines. It is a brick wall that turns galaxy-scale distances into permanent barriers for anything that lives on human or even biological timescales. No matter how you play with energy budgets, no matter how clever your drive is, No matter how much you lean on time dilation, 100,000 light-years of distance puts leaving the galaxy outside the range of any continuous stable civilization even vaguely like ours. And all of this has quietly assumed a perfect clean path. No hazards, no damage, no environment. But real interstellar space is not clean. The moment you try to actually fly through the galaxy at these extreme speeds, every stray atom and every dust grain starts to act like a weapon. So the next question is simple and ugly. What happens when a ship carrying the energy of a planetary scale weapon slams into a single grain of dust at a fraction of light speed? You probably imagine that if you could just go fast enough, the rest is simple. You point the ship at the target and cruise through empty space. The problem is the space between stars is not empty, and the faster you go, the more that almost nothing turns into a weapon pointed straight at you. Inside the Milky Way, the interstellar medium is everywhere. On average, you're looking at a few atoms per cubic centimetre, mostly hydrogen, plus some helium and traces of heavier elements. Mixed into that are tiny solid particles, dust grains a few micrometers across, basically fine sand made of carbon and silicates. At walking speed, that density is nothing. At orbital speed, still nothing. At 10% of the speed of light, those dust grains stop being harmless specks and start behaving like high explosives. Here is why. The energy of a moving object grows very fast with speed. It goes like the speed times itself. Multiply that by relativistic effects at a good fraction of light speed, and even a microscopic grain slamming into your hull at 30,000 kilometers per second dumps an absurd amount of energy into a tiny area in an instant. That does not mean a little ping, it means a tiny patch of your hull suddenly gets heated to plasma, material vaporizes, shockwaves propagate, and fragments rip inward. One grain is bad. Over years of flight through the galaxy, you are going to meet a lot of them. So the obvious next question is, why not just armor up? Why not wrap the ship in heavy protection and take the hits like a tank? We already use a basic version of this idea. Spacecraft today sometimes use Whipple shields, thin outer layers of material placed in front of the main wall. A small impact hits the first layer, vaporizes, spreads out, and the inner wall feels a gentler, wider hit, which it can survive. Tests and real missions show this works for tiny bits of debris at typical orbital speeds. Now scale that to galactic travel speeds. At 10% of light speed, the energy of each impact goes up by many orders of magnitude compared to low Earth orbit. The thin, sacrificial layer you use now would just disappear, and the shock would punch straight through. To stop that, you would need much thicker, much denser shielding. We are no longer talking about a few centimeters of aluminum. We are talking about meters, maybe tens of meters of dense material out front, constantly eroding as it eats dust and gas. That turns your sleek starship into something more like a moving bunker, a huge, blunt block pushing a destructive bow wave in front of it. The mass of that shield alone could dwarf the rest of the vehicle. And remember the rocket problem you just saw. Every extra kilogram of shield needs more propulsion, more fuel, more structure. You get into a loop where adding enough armor to survive the speed makes it harder to reach that speed in the first place. Even if you somehow solve the dust and pebble problem with insane front shields, there is another environment you cannot ignore: radiation. The Milky Way is filled with cosmic rays, high-energy particles, mostly protons and heavier atomic nuclei, flying around at speeds close to the speed of light. We measure them with detectors on the ground and with instruments on satellites and the International Space Station. We know they slam into our atmosphere all the time, creating showers of secondary particles, and that exposure to them is a serious issue for astronauts. On a long trip, even at low speeds, cosmic rays slowly chew through living tissue. They break DNA, they cause mutations, they raise cancer risk, and they also damage electronics by flipping bits or burning out components. Over decades, this is a tough engineering and medical problem. Over centuries or millennia, it becomes a survival problem. You would need heavy shielding, constant maintenance, and probably advanced biology just to keep a crew alive and your systems functioning. So you might say, fine, physical walls are heavy. What about using fields instead? What about building a magnetic shield, like a miniature version of Earth's magnetic field, to deflect charged particles away from the ship? In principle, that idea has something going for it. Earth's magnetosphere does protect us from a lot of solar wind particles, and people have proposed big superconducting coils around a ship to create a protective bubble. The issue is scale. The path of a charged particle in a magnetic field bends, but the higher its energy, the harder it is to curve. Cosmic rays in the galaxy often carry enormous energies, far above typical solar wind particles. To deflect them meaningfully, you need either extremely strong fields or very large distances over which the field can act, and realistically you need both. That means you are now talking about magnets large compared to the ship itself, massive coil systems, and constant power. And that still does nothing about neutral atoms, dust grains, or larger debris. They are not bothered by magnetic fields at all. Worse, the faster your ship goes through the interstellar medium, the more intense the effective radiation and particle flux becomes from your point of view. At high fractions of light speed, you are basically ramming into the thin gas and dust at such extreme relative speeds that it blue shifts and compresses into a deadly cone in front of you. The environment in your path gets harsher, not calmer, the more successful you are at going fast. Put this all together and the pattern is clear. The galaxy is not a quiet background you slide through. It is a minefield that scales with your ambition. At low speeds over small distances, the hazards are manageable. As you push towards serious fractions of light speed, the same interstellar medium that seems like almost nothing at rest becomes a stream of bullets and radiation blasts heading straight at your nose. To survive, you need absurd shields, absurd fields, or both, which then feed straight back into the mass and energy problems you already have from rockets and relativity. And remember, all of this pain is just to move around inside the Milky Way, not to actually escape it. You're paying huge costs in shielding, energy, and risk just to get to speeds that still fall short of the escape velocities set by the galaxy's gravity. So the next logical question hits even harder. If going fast inside the galaxy is already this lethal, what does it actually take to climb all the way out of the Milky Way's gravity well itself? And what kind of object do you have to fight to do that? So what does it actually mean to leave the Milky Way? Not just wander around inside it a little faster. In gravity, leaving is very specific. You have to move so fast and in the right direction that the galaxy can never pull you back. You're not just shifting into a bigger orbit, you are climbing all the way out of the gravity well and never falling in again. That minimum speed is the escape velocity, and it depends on how massive the thing is that is holding you and how far out you are from its centre. You have already seen this on small scales. To get off Earth and never come back, you need a bit more than 11 kilometers per second. If you launch slower than that, you can still get very high. You can orbit. You can go to the moon, but you stay bound to the planet. Add more speed, cross that threshold, and your path changes from a closed loop to an open one. You're gone for good. Now take that same idea and scale it up by many orders of magnitude. Replace Earth with the entire Milky Way. When astronomers count up the mass of the Milky Way, they do not just count stars. They include gas, dust, star clusters, the central black hole, and then something much stranger, dark matter. Once you add it all up, the total mass lands in the range of roughly 1 trillion times the mass of the Sun, possibly more. Most of that is not in the bright disk you see in images. A big chunk is spread out in a huge, roughly spherical halo around the galaxy. All of that mass, visible and invisible, is what your star is orbiting in. That much mass creates a very deep gravitational well. Near the Sun's position, about 27,000 light-years from the centre, the stars around you orbit at about 220 kilometers per second. That number is not a guess. We measure stellar motions and see that rotation pattern. That is the sideways speed the Sun already has just from living where it does. But orbital speed is not the same as escape speed. Just like a satellite in a neat circular path around Earth is still trapped by Earth, A star on a regular orbit around the galactic center is still trapped by the Milky Way. If you want out, you have to go faster than that orbital speed. The local escape velocity from the galaxy, where you are, is estimated to be around 500 to 600 kilometers per second. That is the speed you need, relative to the galaxy, if you want your path to open up so much that you never circle back. Compare that to Earth's 11.2 kilometers per second. Leaving the galaxy from here is not just a bit harder than leaving the planet. It is dozens of times harder in strict speed, and far, far worse in energy. Now remember what your hardware can actually do. Your best chemical rockets get payloads up to on the order of 10 kilometers per second of speed change by themselves. To do better, you rely on clever tricks, like gravity assists around planets and the sun, stacking up small boosts over time. Your fastest probe, Parker Solar Probe, only briefly reaches around 190 kilometers per second by diving deep into the sun's gravity well and whipping around it. And that is for a small, stripped-down machine with no people, minimal shielding, and a very specific trajectory. For a heavy, shielded, crewed ship, getting anywhere near 500 or 600 kilometers per second using anything like current rocket tech is simply not happening. You're at least one full order of magnitude short in speed, and many orders of magnitude short in energy, compared to what you would need to clear the galaxy's grip from your current location. So instead of looking at rockets, look at what nature does when it actually manages to throw something out of a galaxy. Every now and then, astronomers find a hypervelocity star. A star racing away from the Milky Way at hundreds or even close to 1,000 kilometers per second. These are not normal stars. They are outliers with insane speeds compared to their neighbours. The leading idea for how many of them form is simple and brutal. A pair of stars, or a star with a companion, strays too close to the central supermassive black hole. The gravity there is extreme. One member of the pair falls inward and gets captured or torn apart. The other member gets flung outward by the interaction, like a rock being snapped out of a slingshot, but on a galactic scale. You trade one star in, one star out, and the out star leaves with enough speed to possibly escape the galaxy. These stars are not common. They are rare edge cases produced by extreme encounters in the very core of the galaxy, under conditions you cannot reproduce in any controlled way. And even then, many of those stars are only just unbound. They have barely enough speed to escape the combined pull of the visible Milky Way and its dark matter halo. They will spend millions and millions of years climbing out, slowing as they go, before they are truly clear of the galaxy's reach. Think about what that implies for you. A star with the mass of the Sun, launched by a supermassive black hole at around 1,000 kilometers per second, only just manages to exit the galaxy's grip. That is the kind of energy you need to clear the Milky Way's escape velocity from your position. You're not talking about a big rocket launch pad. You're talking about the energy budget of catastrophic one-time events in the galactic core. So if you ask, very literally, how do we leave the Milky Way? The honest answer right now is, only two kinds of things are known to make it out. One, small stars and bits of gas flung by violent gravitational interactions near supermassive black holes. Two, compact objects and debris kicked by supernova explosions and other extreme events. Both are random, destructive processes. None involve navigation, control, or safety. You do not ride these exits, you survive them by accident if you're lucky. And that is the key point here. To really exit the galaxy, you do not just need a fast ship. You need an energy budget on the same scale as the most violent events in the Milky Way, because that is what it takes even for nature to just barely unbind a star. The Milky Way's escape velocity near you is not just a number on a chart. It is a statement about how deep the gravity well is that you live in, and what kind of forces it takes to climb out. But there is a twist that makes this even worse. Everything we have just talked about quietly treated the galaxy as all the stuff you can see plus a bit extra. In reality, the thing holding you in is dominated by something you cannot see at all. A dark matter halo that stretches far beyond the bright spiral arms. So even if you somehow fought your way past the visible Milky Way's pull, you would still be climbing out of an invisible cage that outweighs everything you can see. The obvious question is, how do you escape a prison when most of its mass is literally invisible, and you only know it is there because of how hard it pulls on you? How do you beat gravity from something you cannot even see when most of the pull holding you here comes from matter that does not glow, does not reflect, and barely interacts with anything? That is the part of the prison people forget. The Milky Way is not just stars and gas. It sits inside an invisible cage of dark matter. Start with the basic picture. When you look at images of the Milky Way, or of other spiral galaxies, you see a bright disk, a central bulge, a few fuzzy halos of star clusters. It is natural to think that is the galaxy. But when astronomers track how stars move and how gas clouds orbit, the speeds do not match what you would expect from just the visible stuff. To explain the motions, you have to add a huge amount of extra mass that does not show up in any normal light. That extra mass is what we call dark matter. The shape of that dark matter, as far as we can tell, is not a flat disk like the stars. It is more like a huge, roughly spherical halo centered on the galaxy, stretching far beyond the visible spiral arms. The bright disk you are used to seeing is just the thin, glowing layer embedded in that larger, invisible cloud. When you say I live in the Milky Way, you really mean I live in a rotating disk inside a dark matter halo. How do we know this halo is there if we cannot see it directly? One of the key clues comes from galaxy rotation curves. For a normal spinning system like planets around a star, objects farther out move more slowly. In the solar system, Mercury zips around the sun quickly, Pluto crawls. If you only had the sun's gravity, you would expect something similar in a galaxy. Inner stars fast, outer stars slow. What we actually see in the Milky Way and in many other spiral galaxies is very different. Stars far from the center orbit almost as fast as stars much closer in. The rotation curve stays flat instead of dropping off. If you try to explain that with only the mass of the stars and gas you can see, the numbers do not work. The outer parts should be flying apart. They should not be able to hold their speed, yet they do. The simplest fix is to accept that there is more mass there, spread out over a huge volume that does not shine. When you add that dark matter, the curves line up. The stars are not moving too fast for the galaxy they are in. They are moving at exactly the right speed for the total visible plus invisible mass distribution. You do not see the cage, you see how hard the cage pulls on everything inside it. Now put some size on this. Best current estimates say the Milky Way's dark matter halo holds on the order of 1 trillion solar masses. That means roughly that if you could weigh all the dark matter around the galaxy, you would get a mass about 1,000 billion times that of the Sun. The visible stars, gas and dust are only a fraction of the total. The real gravity well, the thing you are trying to escape, belongs mostly to the dark component. That has a direct, harsh consequence. When you talk about leaving the Milky Way, you're not just talking about slipping past the spiral arms or getting beyond the bright disk. You're talking about climbing out of a dark matter halo that is much more massive and much more extended than the part of the galaxy you can see in any telescope image. The escape speed numbers you heard, the 500 to 600 kilometers per second near the Sun, come from that combined mass, not just from the stars. And dark matter is not just some old theory line in a textbook. New observations keep pointing back to it. For example, gamma-ray telescopes in orbit, like the Fermi satellite, have mapped high-energy light around the Milky Way. They see large, roughly spherical regions of emission above and below the galactic plane, huge bubbles or halos of gamma rays. There is active debate about the exact cause. It might be past activity from the central black hole, or waves of star formation and explosions, or even, in some models, signals from dark matter particles colliding and annihilating each other. The key point for you is not which detailed model wins. The key point is that on large scales, the Milky Way behaves like there is a vast, extended mass distribution shaping how gas flows, how stars move, how high-energy particles are trapped and guided. That unseen mass, whatever its exact particle nature, is real enough to bend orbits, hold onto satellites, and define the size of your gravitational prison. Here is the part that makes this feel different from any normal engineering problem. You cannot mine dark matter. You cannot push off it with a sail. You cannot scatter it with radiation or heat. As far as we know right now, it does not interact strongly with light or with normal matter. It only shows up through gravity, so there is nothing clever you can build to turn it off or weaken it or cancel it. You do not hack the dark matter halo, you just have to pay the full escape energy bill. That means even in the most optimistic future, even if you somehow master fusion rockets, antimatter drives, giant beam propulsion systems, whatever you imagine, the basic requirement stays the same. To leave the galaxy, you have to give your ship or your colony enough kinetic energy to climb out of the combined gravity of stars, gas, and a dark matter halo with a mass of about 1 trillion suns. There is no shortcut and no cheap route. It is all brute force. So add this layer to the picture you already have. The Milky Way's visible disk, the spiral arms, the glowing star fields. Those are not the main bars of the cage. They are just the lit structure sitting deep inside a much bigger, darker potential well. When you say we'll just go beyond the stars, that is not enough. You would also have to outrun their shadow, the gravity of the dark halo that extends far past the last visible star. And that sets up the next step in the trap. Because even if you pretend, somehow, that you pay that insane energy cost and your technology lets you punch out of this dark matter halo, you're still not free. The Milky Way itself is only one member of a larger gravitational family, the local group. A cluster of galaxies all bound together in the same expanding universe. So the real question becomes, if escaping one dark matter halo costs star-scale energy, what does it mean that your entire neighborhood of galaxies is locked together by gravity as well, and that the universe itself is closing in around that island? Here is the next problem. Even if you beat the Milky Way, you are still not free, because the galaxy you live in is not alone. It is part of a bigger lock system that ignores the expansion of the universe on human scales. Zoom out one more level. The Milky Way is one large spiral galaxy, Andromeda is another, Triangulum is a third, and around them swarm dozens of smaller dwarf galaxies. Together they form the local group, a gravitationally bound collection of more than 30 major galaxies, spread across a region about 10 million light-years wide. That whole structure, with all its stars, gas, and dark matter, holds itself together with its own gravity. At the same time, you have probably heard that the universe is expanding, that distant galaxies are moving away from us, that space itself is stretching. So here is the key question. If everything is expanding, why doesn't the local group just drift apart too? Why are we not being pulled away from Andromeda instead of dragged toward it? The answer is simple but important. Gravity can beat expansion on small enough scales. Think of it this way. On the very largest scales, space is stretching and distant galaxy clusters recede from each other. But if a bunch of matter is close enough together and has enough mass, its own gravity wins locally. It stops expanding with the rest of space and becomes a bound island. The local group is one of those islands. Space expands around it, not inside it. The galaxies inside that region move mostly under each other's gravity, not under the push of cosmic expansion. You can see this in the motion of Andromeda itself. Instead of drifting away with the Hubble flow, it is actually moving toward the Milky Way at a few hundred kilometers per second. That alone tells you we are in a shared gravitational pit falling toward each other. Measurements, including precise data from the Gaia mission, are refining the exact numbers, angles, and timescales, but the big picture is stable. The Milky Way and Andromeda are not just neighbours. They're on a long-term collision and merger course over the next few billion years. So the classic story is, in a few billion years, Andromeda and the Milky Way will pass through each other, their stars mostly missing direct collisions because the space between them is huge, but their orbits will get scrambled. Tidal forces will fling gas around, and over time the two spirals will merge into one larger, more elliptical galaxy. Newer data tweaks the details. Maybe the exact head-on path is more of a near miss. Maybe there will be multiple passes, but none of that changes the core fact. We are tightly bound, and the local group is not coming apart. It is condensing. That is what bound against expansion really means. The local group is a stable gravity well, even as more distant structures move away faster and faster. You are not just stuck inside a galaxy. You are stuck inside a small cluster of galaxies that share the same overall fate. The Milky Way, Andromeda, Triangulum, and the dwarf galaxies are like bees caught in the same web, buzzing around a common centre of mass, while the rest of the universe drifts further away on much bigger scales. Now bring back the earlier sections. You've already seen how hard it is to get out of the Milky Way's disk, and then out of its dark matter halo. Suppose somehow you pay that cost. You accelerate ships to insane speeds, you survive the interstellar shrapnel, you climb out of the halo's gravity, and you are genuinely unbound from the Milky Way. Where are you now? You're not in some calm open universe, you're in the deeper gravitational pocket of the entire local group. The mass that binds the local group is larger than the mass of the Milky Way alone, by a lot. It includes Andromeda's dark matter halo, Triangulum's halo, and the halos of all the dwarves, plus the shared extended dark matter structure that ties them together. The escape velocity from that combined system, from somewhere near its centre, is even higher than the escape speed from a single galaxy. So, escape the Milky Way is really just step one of a much tougher problem. The local group does not let go easily. This is where the second box idea hits. Think of the Milky Way as your house. Escaping it is like blasting through the walls, using ridiculous energy, surviving debris, and getting out into the street. You might feel free for a moment, but when you look around, you realise the entire street and the neighbouring streets are inside a much larger walled city, and those outer walls are taller and farther away than your house ever was. That larger box, in your real situation, is the local group. So in practice, if you build ships that actually can leave the Milky Way, what happens to them? With current physics, they are not going to cruise off into the wide open. They are going to end up in different orbits inside the local group's potential well. Most realistic escapes from the Milky Way would simply mean you fall toward another local group galaxy. Maybe you end up captured by Andromeda, or you drift toward one of the dwarf galaxy's halos, or you move on a long, looping path around the combined mass of the group. That is the depressing twist. For a civilization like ours, intergalactic travel mostly turns into interlocal group travel. You're not hopping between truly separate island universes, you are just moving around inside your own local island. The real border of your long-term cosmic neighbourhood is not the outermost stars of the Milky Way. It is the scale where the local group's gravity finally loses to cosmic expansion. And here is the part that connects straight back to the main theme. When people say leave the Milky Way, they imagine a clean final exit, a path that takes you out into some neutral background where you can go anywhere. What the physics actually says is, even if you throw ridiculous amounts of energy at the problem and beat the galaxy's own gravity, you are still caught in a deeper net. The universe has already drawn borders around you, using mass and expansion, and those borders do not care about your technology level. So the best you can realistically say is, maybe, someday, a civilization gets powerful enough to move between galaxies inside the local group. But that is not freedom on a cosmic scale. That is just moving between cells inside the same larger prison. And all of this still assumes your species, your culture, and your technology can remain coherent and stable over the mind-bending timescales these journeys would demand. Which brings up the next, very uncomfortable question. Even if you had the engines, the shield, and the energy to try any of this, can biological life like you actually function on timescales of hundreds of thousands to millions of years? Or does biology itself, with limited lifespans and fragile ecosystems, quietly kill the dream of leaving the galaxy long before gravity does? How do you plan a trip that takes longer than your entire species has existed, when your body is built for less than a century, and your mind is built for days, months, maybe decades at most? This is the moment where the physics problems you have heard about smash into biology, and biology simply cannot keep up. Start with basic numbers. Your lifetime is on the order of 80 to 100 years, if medicine goes well. The Sun's orbit around the Milky Way takes about 220 million years. A beam of light moving at the cosmic speed limit needs around 100,000 years to cross the disk. Put those side by side and you see the gap immediately. One human life is a tiny slice of one orbit, and an even smaller slice of a galaxy-crossing light trip. You are not built for these scales. You live and die before any galactic scale event even moves a noticeable amount. So you ask the obvious question, if you cannot stretch a single lifetime to match the trip, can you at least survive a small part of it safely, outside your protected bubble on Earth? This is where radiation shows up, and it is not optional. On Earth's surface, you are shielded by the atmosphere and by the planet's magnetic field. They block most high-energy particles from the Sun and from deep space. Astronauts on the International Space Station, who sit above most of that shield, already take in much larger radiation doses than people on the ground, even on missions that last only months. Now extend that to centuries. Out between the stars, you are exposed to a constant flow of cosmic rays, solar particle events, and high-energy photons. Without serious shielding, those will hit your DNA again and again, causing breaks and errors that your cells cannot fully repair. Cancer risk rises, tissue damage accumulates, and over long enough times, the dose is lethal. It is the same story for electronics. Cosmic rays can flip bits, corrupt memory, and damage circuits over time. A ship trying to run for thousands of years is facing a steady sandblasting of its hardware and its crew at the particle level. So maybe you think, fine, we'll not try to keep one person alive for the whole trip, we will build generation ships. These are large habitats, moving through space for thousands of years, where people live, have children, grow old and die, while the ship slowly crawls to its destination. The idea sounds flexible, but then you have to keep a closed ecosystem stable for absurd lengths of time. On Earth, we have tried small versions of this, sealed habitats where people recycle air, water and nutrients. Projects like biosphere experiments showed how hard this is even for a few years, under careful monitoring with emergency support right outside the door. Tiny imbalances in gas levels, microbes, nutrient cycles or mechanical systems grow into real problems fast. Now imagine scaling that to a moving habitat that has to work for 10,000 years, with no resupply, no outside repair crews, and no guarantee that your descendants will keep the systems perfectly tuned. On top of that, you have human behaviour. A generation ship is not just a machine, it is a society trapped in a metal tube. You have to assume that culture remains stable, that knowledge is preserved, that people keep caring about a mission their ancestors started long before they were born. Even over a few hundred years of history on Earth, cultures transform dramatically. Over thousands of years, on a ship cut off from the rest of humanity, you're almost guaranteed to see big shifts in beliefs, priorities, and willingness to follow a centuries-old plan. Maybe you try to dodge these issues by skipping the middle part. Instead of living through the journey, you freeze people, or you slow their aging so much that they can ride out long flights in a single body. Right now, that is still almost entirely in the realm of speculation. Cryobiology can freeze and revive some simple organisms and preserve small tissues and embryos. But safely freezing a complex mammal, especially a human, and bringing them back with their brain intact, undamaged and functional is something we cannot do. Longevity research does push life expectancy upward, with better medicine, better control of disease and possible drugs that tweak aging pathways. But you are talking about adding years, maybe a few decades, not multiplying lifespans by a factor of 1,000. There is no real path in present science that takes a human body that tops out around 100 years and turns it into something that calmly lives for tens of thousands of years. And even if far in the future some form of life extension or suspended animation works, it comes with its own risks. You would be betting everything on medical and technical systems that have to run flawlessly for the entire duration of the journey. Any failure in the middle, any power loss, any shielding issue could mean you simply never wake up, or you wake into a ship that is damaged beyond repair, so you end up in a corner. Classic human biology gives you lifespans that are tiny compared to galactic travel times. Radiation tears at the body and the ship over decades. Closed ecosystems are fragile and hard to balance even now at small scale. With full support, cryosleep and radical life extension are still at the early idea stage, and even if they become real, they demand perfect engineering over timespans no human institution has ever managed. That pushes you toward a harsh conclusion. If you really want to plan trips on the scale of the Milky Way, life as you know it is the wrong tool. You would need to redesign it, move to heavily engineered humans or synthetic organisms, or even fully non-biological minds that do not care about radiation the way DNA does. Or you accept that the thing arriving at the far end of a galactic-scale journey after tens of thousands or hundreds of thousands of years is not the same species that left. It is a descendant, mutated by environment, by culture, by drift, by deliberate editing. So when people talk about we will leave the galaxy under the rules set by biology, that statement quietly hides a lot of loss. It means the ones who launch will never see the destination, their direct culture will not survive the trip, and the beings who arrive may not even think of themselves as the same us anymore. And that is before you count the energy cost of driving the ship, the maintenance of megastructures, and the slow decay of any human-made system over cosmic time, which leads straight to the next big barrier. Even if you solve biology, even if you build generation ships or redesign life, there is still the raw energy bill to move anything massive at serious fractions of light speed. And when you calculate that bill honestly, you realize something uncomfortable. To move at the speed you would need, you do not just need a rocket, you need the output of a star. How much power do you really need? If your plan is not just to leave a planet, not just to hop between stars, but to try to beat an entire galaxy's gravity? The honest answer is, you stop thinking in terms of power plants and fuels, and you start thinking in terms of stars. Take the sun. Every second it throws out around 4 times 10 to the power 26 watts of power. In normal words, that is hundreds of thousands of billions of joules of energy every single second for billions of years. That is your local energy giant. All your rockets, all your power stations, all your global civilization are tiny ripples on top of that flow. Humanity today runs on a total power of roughly 10 trillion watts. That sounds huge until you compare it to the sun. The sun outshines your entire civilization by a factor of about 10 trillion. If you want to seriously talk about star-crossing or galaxy-crossing ships, you're not going to do it with chemical fuel and a few reactors. The only realistic energy reservoir big enough is the output of a star itself. That is where the Kardashev scale comes in. It is a simple way to rank civilizations by how much power they can use. A Type 1. Civilization taps most of the energy available on its home planet, from sun, wind, heat, everything. A Type 2 civilization goes further and captures a significant fraction of the total power of its star. The usual image is a Dyson swarm, not solid shell, but a huge cloud of solar collectors, habitats and mirrors orbiting the star, catching a large part of its light and turning it into useful energy. If you want to push large ships to serious fractions of light speed, that is the level you are talking about. You're not wiring a few panels together. You're building a structure of millions or billions of collectors, coordinating them and channeling star-scale power into beams or drives. And right now, when we look with our telescopes at nearby stars and galaxies, we do not see obvious, clean examples of these swarms. Surveys in infrared light, which would pick up the waste heat from such megastructures, have not turned up clear signs of Type 2 civilizations in our neighborhood. Now, connect this to the energy cost of moving a real ship. Earlier, we talked about a 1,000-ton starship at 10% of light speed carrying kinetic energy comparable to many centuries of total human energy use. That is just the energy stored in its motion. You also have to account for inefficiencies, for the energy you spill as heat, for losses in your engines and power systems, and that is only for a modest ship, not a full mobile city or ecosystem. If you want to accelerate something much bigger, something city-sized, to a serious fraction of light speed, and then slow it down again at the destination, you quickly get into absurd territory. Depending on your exact design, you're using up the equivalent of years, decades, maybe centuries of the sun's entire power output just to push one chunk of mass to speed and then kill that speed safely. If you do not have access to star-scale power, you are stuck. If you do, you still have to manage it, control it, and not vaporize yourself in the process. There is another catch. You never get perfect efficiency. Any real system that processes huge amounts of energy has to dump waste heat. Engines get hot, collectors get hot, beams scatter. All that energy has to go somewhere, and it usually ends up as lower temperature radiation in the infrared. That means a civilization that is capturing a big fraction of a star's light and turning it into directed power would unavoidably glow differently than a normal star system. It would be dimmer in visible light and brighter in infrared. This is not just theory. Space telescopes like WISE have scanned the sky in infrared, looking at millions of sources, including whole galaxies. People have looked for stars and galaxies that seem to be shrouded in warm dust or radiating more infrared than normal for their type, which might hint at large-scale engineering. So far, we do not see clear, unambiguous signatures of civilizations wrapping whole stars or whole galaxies in energy-collecting structures. There are interesting oddballs, but nothing that screams, here is a culture using a big chunk of its galaxy's power output. Now think about what that implies for galaxy-leaving projects. If it was straightforward for an advanced species to build engines that can routinely fling city-sized ships to high fractions of light speed, they would need to move star-level power around again and again. Their infrastructure would leak infrared light. Their stars might look dimmer in normal light and hotter in the mid-infrared. At galactic scale, a civilization that seriously tries to move large amounts of mass out of a galaxy, or between galaxies, would have to process so much energy that it would be very hard to stay hidden from our surveys. Yet when we look, we mostly see normal galaxies, with normal star formation, normally dust, normal rich. If galaxy leaving were common, the sky should look different. We should see entire regions where stars are partly cloaked by swarms of collectors, or where the energy signature of a galaxy is shifted in a way that is hard to explain with natural processes alone. Instead, what we see is a universe where gravity, dark matter, and expansion dominate the big picture, and any engineering, if it exists, is either extremely rare or hiding under the noise of natural astrophysics. This does not prove that nobody anywhere has ever built star-scale machines, but it strongly hints that if such projects happen, they are not frequent and they are not simple. The energy hurdle is not just large compared to current human technology, it is galactically large. It is on the order of reorganize a big slice of a star's total output for a very long time. So stack this on top of everything you already know. The rocket equation is punishing, the speed of light is a hard limit. Interstellar space itself becomes dangerous when you go fast. Biology cannot handle the timescales, and to brute force your way through all of that, you need the power of a star, maybe multiple stars, harnessed with precision for thousands of years. And even if you somehow manage all that, you still have one more brutal problem: you have to aim. Because while you are trying to cross tens of thousands of light years, nothing in the galaxy sits still. Stars move, spiral arms twist, dark matter tugs on everything, and space-time itself is curved. So the next question is, even if you had the energy of a star in your hands, how do you navigate a moving, warped galaxy for a journey that outlives your whole civilization? How do you aim for a target when everything between you and that target is moving, twisting, and drifting for millions of years straight? That is the navigation problem on galactic scales, and it is not a side issue, it is fundamental. You are not flying through a fixed map, you are flying through a system that is constantly rearranging itself. Start simple, nothing in the Milky Way sits still. The Sun is orbiting the galactic centre at about 200 plus kilometers per second. The spiral arms are not solid objects, they are patterns of density that stars and gas move through. Individual stars have their own motions on top of the overall rotation, drifting inward or outward a bit, bobbing up and down through the disk. Gas clouds are flowing along complex paths. Even the dark matter halos is not perfectly static. It has structure, clumps, and streams. When we measure star motions in detail and plot them as arrows across the sky, you get proper motion maps where everything is sliding in different directions at different speeds. It looks calm in a single still image, but in motion it is like watching a slow, three-dimensional traffic jam where every lane is curving and the road itself is bending. Now stretch that out in time. Over a few years, these motions are tiny. Over millions or hundreds of millions of years, they add up. On those long timescales, small gravitational nudges from passing stars, giant molecular clouds, spiral arm crossings, and tidal forces from the rest of the galaxy all start to compound. The orbits of stars are not perfectly smooth circles, they wander. This is what people mean when they say orbits can become chaotic over long periods. Chaotic does not mean random in one instant, it means that tiny differences in starting conditions grow into big differences later. If you try to predict where a specific star will be 200 million years from now, any small uncertainty in its current position and velocity becomes a huge uncertainty in its future location. Your forecast gets fuzzy, then useless, long before the timescales you need to cross a serious chunk of the galaxy. On top of that, space itself is not a flat, empty canvas. General relativity tells you that mass and energy curve space-time. In the Milky Way, you have the central supermassive black hole curving space strongly in the core. You have dense spiral arm regions with extra mass. You have the dark matter halo shaping the overall gravitational potential. Put it together, and the straight line path is not actually straight in any simple sense. It is a geodesic in curved space-time, and that geodesic changes if the mass distribution changes. For you as a navigator, that means there are no fixed intergalactic highways, no permanent straight corridors you can just lock onto and forget. Any long trip is a path through a shifting gravitational maze. If a big mass clump moves, or you pass near a giant cloud, or the galaxy's structure evolves while you travel, your best pre-computed path stops being optimal, and maybe even stops being safe. Now bring in some real data, because we are not guessing about these motions. The European Space Agency's Gaia mission has been mapping the positions and velocities of more than 1 billion stars in the Milky Way with high precision. It gives you a three-dimensional moving picture of part of the galaxy. From Gaia's data, you can see stellar streams where old star clusters and dwarf galaxies have been torn apart, long rivers of stars wrapping around the galaxy. You see groups of stars sharing common motion, traces of past mergers, and evidence that the disk is warped and vibrating. This is already a huge leap in understanding, but it is still only a fraction of the galaxy. 1 billion stars is impressive, but the Milky Way holds hundreds of billions. Even for the stars Gaia does measure, you get precise data over decades, not over millions of years. You can extrapolate their motion forward, but those predictions sit on top of all the chaos and uncertainty we just talked about. So imagine you are planning a mission that takes, say, 100,000 years, which is still less than the light crossing time of the galaxy. You plot a path using the best available map when you launch. You aim for a destination star or a region near the edge of the disk. By the time your ship has gone a serious fraction of the way, several things have happened. The destination has moved. The masses along your path have moved. The overall gravitational field has shifted, even if only slightly, and your own tiny navigation errors, uncorrected over long periods, have grown. You might say, we will update the path during the trip. That sounds fine on human scales, but now remember the communication limits you already saw. If you're tens of thousands of light years away, any message from home with better data takes tens of thousands of years to reach you. By the time you get the new map, it is already out of date again. You cannot rely on ground control to feed you fresh corrections every few years. On galactic scales, there is no tight feedback loop. You're almost always flying on stale information. You can try to make the ship completely autonomous, with onboard sensors that constantly map the local environment and adjust the trajectory. That helps with nearby hazards, like gas clouds or stars you did not expect. but it does not fix the deeper issue that your long-term target is not a fixed marker in a stable potential. It is another moving object inside a dynamic curve system, and your ship is tiny compared to the forces shaping that system. So the core navigation problem becomes this. You need to plan and execute a path through a galaxy where, over the time your trip takes, the very structure you planned through is evolving. The longer your journey, the more the initial map fails you. Over galactic distances and galactic times, the map is always outdated. The best you can do is aim for broad regions, not specific points, and accept that your arrival conditions will be very different from what you started with. Combine this with everything else: limited lifespans, radiation, insane energy needs, dangerous interstellar medium, dark matter gravity, local group binding, and you get a clear pattern. Every layer of reality you look at, from small-scale biology to large-scale dynamics, is pushing against the idea of stable, controlled, galaxy-crossing travel. There is one more brutal limit that ties directly into navigation and control, even if you somehow get a ship moving, and even if you somehow keep it on course, you still have to accept that it will be cut off. Over tens of thousands of light years, communication becomes so slow and so weak that you cannot fly by wire from home. Messages crawl along behind you at light speed, and the signal fades into noise. So the next question is, what does leaving the Milky Way really mean if, long before you reach the edge, you can no longer talk to anyone behind you at all? How do you run a mission when every "hey, how's it going out there" takes longer than your entire civilization has been around? That is what communication looks like once you push out toward the edge of the Milky Way, and beyond that toward intergalactic space. Even if you solve engines, shielding, biology and navigation, the line back home snaps long before you get anywhere near free. Start with pure delay. Right now, talking to a probe at Mars can take minutes. Talking to something at the edge of the solar system takes hours. Stretch that to the Milky Way. From where you are, a light signal to the galactic center takes more than 25,000 years. To the far edge of the disk, you're looking at on the order of 100,000 years. That is for a one-way signal. A simple "are you there?" and a "yes, we're fine" round trip is already longer than the age of agriculture on Earth. Push into intergalactic distances, and the delays jump to millions of years. One way. Any message you send is basically a time capsule addressed to whoever happens to exist in that region when the light finally gets there. So forget about live control. There is no real-time steering from mission control. There is no "we saw something on your cameras, adjust course by 2 degrees. By the time your correction arrives, the ship has moved thousands of light years past that point. Every command you send is based on an old snapshot, and every reply you get describes a world that no longer exists. Then there is bandwidth. It is easy to say, "we'll just use powerful lasers," or "we'll use tight radio beams," but physics sets hard limits. When you transmit any signal, the energy spreads out as it travels, the beam widens, and the power per square meter drops. The farther away your receiver is, the fainter your signal becomes. That means, if you want a high bandwidth link over tens of thousands of light years, you have to do two things: pump out ridiculous transmitter power and build enormous receivers with huge collecting areas. You can do clever tricks like narrow beams, adaptive optics, and coding schemes that squeeze more information into fewer photons, but you cannot dodge the basic fact that long-range, high data rate communication is expensive in energy and hardware. Right now, even with modest distances inside our solar system, deep space missions rely on giant dishes, extreme sensitivity, and relatively low data rates compared to what you are used to with your home internet. Scale that up to galactic distances, and the numbers stop being reasonable for constant rich communication. You end up with occasional slow drips of data, not smooth video calls. On top of spreading and power, you have to deal with noise. The universe is not quiet. The cosmic microwave background is a constant bath of low-level radiation everywhere. The galaxy itself emits radio waves from gas clouds, from energetic electrons spiraling in magnetic fields, from all sorts of natural processes. That creates a noise floor, a background level your signal has to stand above to be detected and decoded. If your signal gets too faint compared to that flaw, it is just lost in the hiss. We are already up against this with current probes. Space agencies have to carefully pick frequencies, power levels, and coding strategies so a tiny spacecraft signal is still visible against the noise when it reaches Earth. That is over distances of billions of kilometers, not tens of thousands of light years. If you try to talk to a small ship on the far side of the galaxy, you are fighting both the inverse drop in signal strength and the noisy radio mess of the galaxy itself. You can try to fix this by throwing more resources at the problem, build truly huge receiving arrays, build many synchronized dishes across light years, pour absurd amounts of power into your transmitters. But that loops back into the same energy budget issues you saw earlier. A civilization that maintained strong, high bandwidth links with ships halfway across the galaxy would be spending star-level power just on communications infrastructure. And remember, everything, ship and home, is moving the whole time. So you also have to track and aim narrow beams very precisely over thousands of years through changing gravitational fields. Then there is the part no antenna can fix, the social and cultural delay. Suppose you launch a mission that heads towards the edge of the galaxy. It travels for, say, 50,000 years. During that time, you send occasional messages, and it sends some back. Every message is staggered by tens of thousands of years. The people who started the project die. Their descendants die. Languages drift. Nations appear and disappear. Maybe your whole civilization collapses and rebuilds multiple times. By the time a "we made it" checkpoint 3 ping arrives back home, the original culture that cared about that checkpoint has been gone for a very long time. From the ship's point of view, any reply they ever get is from a world that has moved on without them. From home's point of view, any status report from the ship is a ghost voice from an ancient project that no one alive remembers authorizing. Institutions do not last that long. So even if you solve the technical problem of sending a signal, you do not solve the meaning problem. Who are you talking to? Who is on the other end of that link? This is what decoherence of culture really looks like on cosmic scales. The shared story that ties us back home to us on the ship falls apart. The travelers adapt to life in transit, maybe in a closed ship ecosystem, maybe in some modified form. The people at home adapt to new conditions on their planet or in their local space. After enough time, they are no longer a single we, they are just two branches of a tree that stopped touching ages ago. Communication, even if it is technically possible, becomes an exchange between strangers with a common ancestor, not a conversation inside one civilization. And remember, this breakdown happens long before anyone is actually clear of the galaxy. You lose real-time control almost immediately once you leave the local neighborhood. You lose meaningful two-way dialogue on human timescales once you are a few thousand light years out. By the time you are genuinely on a path that might leave the Milky Way's halo, any message home is a historical artifact, not a conversation. So you end up with a harsh split. There are two separate problems: physically leaving and staying in contact. The first one is already nearly impossible with what we know about rockets, energy, and gravity. The second one is even worse on cosmic scales, because the galaxy itself cuts your communication threads by sheer distance and light speed delay, long before you reach any kind of outside, which leads to a deeper point. If you cannot keep control, and you cannot stay in touch, who is actually doing this journey? Is it still you, your civilization, your species? Or is it just a one-time fragment spun off into the dark, left to become something else entirely? And if that is true, then maybe the real bottleneck in galaxy leaving is not just physics, but the fact that civilizations, as we know them, do not survive long enough and do not stay focused long enough to carry projects across millions of years. How do you run a project that has to stay on track longer than your entire species has existed? When you stack human history against galactic time, the answer is you don't. The galaxy is not just big in space, it is big in time. And that kills the idea of we'll just keep a civilization going until we leave it. Look at the numbers. Homo sapiens, as a species, has been around for roughly 300,000 years. That sounds ancient from your point of view, but set it next to the Milky Way, which is more than 13 billion years old. Your entire existence is a little sliver at the very end of the galaxy's timeline. Now zoom in further. What you think of as technological civilization, cities, writing, industry, electricity, digital tech, is only a few thousand years old at most, and modern high-tech society is maybe a couple of centuries deep. So you have a species that has barely been around for a fraction of a galactic heartbeat, and a technological phase that is a tiny fraction of that. Against that, you're talking about journeys, megastructures, and long-term plans that have to survive for hundreds of thousands, millions, maybe tens of millions of years. Already the mismatch is obvious. Now look at your actual track record. Civilizations rise and fall all the time. Empires grow, centralize, build roads, aqueducts, libraries, and then collapse. Languages split, merge, and die. Knowledge is discovered, then lost, then rediscovered centuries later from scratch. You can literally point to technologies that were known in the ancient world, certain concrete formulas, mechanical devices, even basic sanitation systems that disappeared for long stretches and had to be reinvented. And all of that chaos is happening on timescales of hundreds or thousands of years, not millions. Extrapolate that forward. Imagine trying to keep one unified project alive with consistent goals and continuous funding over 1 million years. That is already longer than all recorded history by orders of magnitude. Now compare that to crossing even a fraction of the galaxy at any remotely realistic speed. The mission clock and the civilization clock are not even close to synced. This feeds straight into the Fermi paradox, the puzzle of if advanced civilizations are possible, where is everybody? We look out at the galaxy and we do not see obvious signs of engineered structures on stellar scales, no clear Dyson swarms, no galaxy-wide networks lighting up the sky. One usual answer is maybe they are rare, or maybe they do not want to be seen. But there is another angle. Maybe they do not last long enough, or stay stable enough to ever reach that level. Think about all the constraints you have already seen. Energy, radiation, biology, navigation, communication. Now add the social layer. You need a civilization that not only gets technologically advanced, but also stays advanced, avoids wiping itself out, avoids collapse into long dark ages, avoids drifting so far culturally that it forgets why the project started, and keeps doing maintenance on insane infrastructure for time spans that make human history look microscopic. That is a very narrow path. And that brings you to the maintenance problem. Even on Earth, just keeping a global power grid running is hard. Parts wear out, lines break, storms knock in for a structure down, people make mistakes, funding runs out. You're constantly repairing, upgrading, and fighting decay. Now scale that up to mega structures that harvest a star's energy, or beam power across light hours to accelerate starships, or maintain giant lasers and arrays for thousands of years. Every piece of that system is subject to failure. Materials fatigue, orbits drift, micrometeorites hit, software rots if it is not constantly updated, people retire, institutions change, priorities shift. A single civilization might manage to keep something huge running for a few centuries if it really focuses. But for millions of years, with no break, no collapse, no loss of engineering knowledge, that is a different level of difficulty. Even if you imagine automation doing the day-to-day maintenance, you still need someone to design the systems, check the automation, correct for rare but catastrophic events, and decide to rebuild when something fails completely. That means you need a continuous chain of decision-makers and engineers who all agree that this galaxy escape infrastructure matters more than anything else for longer than any human culture has ever stayed stable. So there is a brutal possibility here. Maybe the reason you do not see galaxy-spanning structures is not just that the physics is hard, but that the social and biological side fails first. Civilizations might reach a certain tech level, start ambitious projects, then hit internal limits, resource depletion, climate problems, war, cultural fragmentation, loss of interest, and those projects stall or fall apart long before they reach "we are leaving the galaxy" levels. In that view, the Milky Way is not empty of mega-civilizations because they never existed, but because they are short-lived compared to the galaxy. They flare up, leave some traces, maybe send some probes, maybe build local megastructures, then fade or transform into something else. Over billions of years, the galaxy just keeps rotating, stars keep forming and dying, and those brief bursts of intelligence barely register in the overall structure. This loops back to your own situation in a very direct way. When you say we will leave the Milky Way, you are really saying we will keep a high-tech, coordinated, long-term civilization running for timescales that are enormous compared to anything we have ever done, while also managing all the hard physics at once. The galaxy will still be there either way. It does not need you, but your civilization has to outrun its own tendency to fragment, forget, and reset. So the phrase, "we will never leave the Milky Way," might not be a dramatic, absolute law of nature. It might simply be a realistic statement about how long complex societies can stay focused on one goal. The galaxy outlives every story you are capable of telling, every culture you can build. On those timescales, your entire history is just noise, and even if somehow something like you or descended from you solves all of that, keeps a civilization stable, builds star-scale engines, survives radiation, handles navigation, accepts communication loss, there is still one more layer of prison wrapped around everything. The universe itself is expanding, and that expansion draws a boundary far beyond the Milky Way, a horizon that slowly cuts you off from the rest of the cosmos forever. So the final question is not just can you leave the galaxy, but even if you did, would the expanding universe simply lock you into a new, smaller island anyway? How do you escape the universe itself when the space between you and everything else is literally stretching faster than you can ever travel? At some point, the problem stops being, how do we leave the Milky Way, and becomes, how do we outrun the expansion of space? And the answer there is brutally simple: you do not. Start with the basics. On very large scales, galaxies beyond our local group are moving away from us. The farther they are, the faster they recede. This pattern is described by something called the Hubble constant. The key idea is this: space itself is expanding. It is not that galaxies are all firing rockets and flying through a static background. The background, the fabric of space, is stretching, and the galaxies are mostly just riding that expansion. If you put two galaxies in this expanding space, the space between them grows over the time, so they get farther apart. The more space between them, the more stretch you get, so the faster they seem to separate. That is why a galaxy twice as far away recedes roughly twice as fast. This is built into the large-scale structure of the universe. Gravity can locally hold regions together, like galaxies and the galaxy groups, but beyond those scales, expansion wins. Now here is the part people often miss, because expansion is accelerating, driven by what we call dark energy. There is a hard limit to where your influence can reach. That is the cosmic event horizon. There is a distance beyond which, no matter what you do right now, any light you send, any signal, any ship will never reach. Space between you and that region is expanding so fast that even light, moving at its maximum speed, cannot make forward progress in the long run. The expansion outruns it. That means there is a growing too late boundary written into the universe. Anything already beyond that horizon is effectively gone forever, causally disconnected. You can see some of it now because of old light that left those regions long ago, when they were closer, but anything you emit now will never get back there, and anything they emit now will never get to you. The accessible universe, the part you can actually affect, is finite. Project this into the far future. Right now, we live in a universe where we can still see billions of galaxies. But as time goes on, cosmic expansion keeps stretching space, and more of those galaxies cross the event horizon. Their light gets redshifted, stretched to longer wavelengths, and eventually fades out of detectability. In tens to hundreds of billions of years, most of the galaxies we see today will have slipped beyond the horizon. They will still exist, but they will no longer be visible, and no signal from us will ever reach them, what stays with us? The things that are gravitationally bound strongly enough to resist expansion, basically the local group and whatever it merges into, the Milky Way, Andromeda, Triangulum, and the dwarf galaxies will collide and merge over very long times, forming one large island galaxy or galaxy remnant. That island will still be held together by its own gravity, while the rest of the universe races away faster and faster outside. So in the deep future, an observer inside this merged system will look out and see almost nothing. No bright web of galaxies, just their own local structure, floating in a dark, empty-looking cosmos. For them, the entire reachable universe will have shrunk down to that one gravitationally bound clump. Everything else will be beyond the cosmic horizon, not just far away, but fundamentally unreachable in principle. Now, plug your galaxy escape story into this picture. Suppose some ridiculously advanced civilization, far smarter and more capable than us, actually manages to leave the Milky Way. They pay the insane energy costs, they build star-scale engines, they solve radiation, they handle navigation, they accept communication loss, they move out into the halo, maybe even climb fully free of our galaxy's gravity well. What next? On long timescales, they are still trapped inside the local group island. The local group's gravity is strong enough that expansion does not tear it apart, so their bigger escape options are limited to moving between members of the group, which themselves are going to merge anyway. They cannot ride expansion outward to jump to the next cluster, because beyond a certain radius, expansion is not a slow drift, it is a one-way barrier. There is no path, even at light speed, that reaches beyond the event horizon once it is drawn. That gives you a harsh twist on the whole idea. Leaving the Milky Way is not the same as leaving the cosmic prison. On ultra-long timescales, the maximum territory any civilization can ever realistically influence is a single gravitational island like the local group. That is the island universe that will still be visible and reachable after everything else has been pushed away by dark energy. So even if you imagine some god-tier society that laughs at our current engineering problems, that masters propulsion, that builds Dyson swarms, that handles million-year planning, physics still draws a line around them. Not at the edge of their galaxy, but at the boundary where expansion turns into an uncrossable gap. Beyond that, the universe is there in theory, but gone in practice. Put that together with everything else. You are held in place by the Milky Way's gravity and dark matter halo. You are nested inside the local group's deeper gravity well, and the whole system sits inside a universe where dark energy is gradually shutting down long-distance communication and travel outside your local island. The Milky Way is not just a hard object to leave, it is an object inside an even bigger structure that is also being locked in. So the real picture looks like this. You're born in a galaxy-sized prison that sits inside a group-sized prison, inside a universe that is slowly walling off everything beyond that group forever. Physics does not just cage you in a galaxy, it cages the galaxy itself in a shrinking bubble of what is reachable. At this point you might ask, if normal controlled exits are this hopeless, are there any ways the universe actually does throw things out of galaxies? And yes, there are, but they do not look like travel. They look like disasters, stars and black holes hurled out by violence, not by design. So the next question is, if nature's only proven exits from galaxies are catastrophic slingshots, what does that say about our chances of ever building a gentle, steerable version of that for ourselves? What if the universe's only working tickets out of galaxies are so violent you would never survive using them on purpose? That is the kind of exit strategy nature actually uses, and it looks nothing like a controlled starship burn. Start with the things we have actually seen leave galaxies, hypervelocity stars. Astronomers have found stars moving at hundreds, sometimes close to 1,000 kilometers per second on paths that carry them out of the Milky Way entirely. These are not gentle drifters. Their speeds are way above the normal orbital motion of stars in the disk. At those speeds, they are not just in a big orbit, they are on open trajectories that will carry them into intergalactic space over millions of years. The leading explanation is simple and brutal. Take a binary system, 2 stars orbiting each other, or a star with a compact companion, and send it on a close pass near the central supermassive black hole. The gravity there is extreme. One object gets captured or torn apart, the other is flung outward, trading its partner for a massive speed boost. You end up with a star that has effectively been shot out of the galactic centre like a bullet. No engines, no planning, just raw 3-body chaos in a very deep gravity well. The important point for your question is this: that star has technically done what you dream of. It has reached, or nearly reached, galactic escape velocity. Given enough time, it will climb out of the Milky Way's potential and travel through the emptiness between galaxies. So the laws of physics absolutely allow matter, even whole stars, to leave galaxies. It is not forbidden. It just happens through rare, violent fluke events, not by design. There is an even more extreme version: runaway black holes. Observations have turned up cases where it looks like a supermassive black hole has been kicked out of the centre of a galaxy at thousands of kilometres per second, sometimes dragging a trail of newly formed stars behind it. The likely causes are major mergers between galaxies or interactions between multiple black holes in a tight region. Gravitational waves and complicated orbital exchanges can give one black hole a huge recoil kick, enough to sling it right out of its home galaxy and into intergalactic space. That is the scale of violence the universe uses when it punches a hole in a galaxy. You're talking about events where entire star systems are shredded, where orbits are scrambled, where a black hole with millions of solar masses gets shot out like a cannonball. It proves that, in principle, you can overcome a galaxy's gravity, but only by spending unbelievable amounts of energy in completely uncontrolled ways. Now ask the obvious question: could you ever ride something like that? Could a civilization somehow park a ship near a black hole, set up the right orbit, and use a close pass as a gravitational slingshot to reach escape speed on purpose? On paper, you can write down trajectories where a small object steals energy from a bigger system and leaves at much higher speed. Gravity assist maneuvers inside the solar system already do a mild version of this around planets. The problem is, near a black hole, the margins are almost non-existent. If you pass a little too far out, you do not get enough of a kick. If you pass a little too close, tidal forces rip you apart, or you fall inside the event horizon and never come out. There is no gentle gradient here. One side of the tiny safe corridor is pointless and slow, the other side is death. And this is before you consider all the radiation, hot gas, and high-energy particles blasting around the black hole's environment. On top of that, you do not control the black hole's partners. The whole reason these kicks are so strong is that multiple massive objects are interacting in a tightly bound, chaotic system. Trying to time your tiny ship to use that interaction without being destroyed is like trying to surf on 2 colliding tsunamis while aiming for a specific rock on the beach. The physics allows some particles, some stars, some black holes to come out fast. It does not offer a safe lane for you. So yes, nature has escape pods from galaxies, but they are not pods you want to sit in. Hypervelocity stars do not steer where they go. Runaway black holes do not care what they smash through on the way out. These are not vehicles, they are debris. Using them as a model for human travel is like using a building demolition as a model for how to walk through a doorway. And this is the pattern that keeps showing up. When you look at every real way the universe moves things around at galactic speeds, black hole kicks, slingshotted stars, tidal stripping of whole systems, they're always catastrophic. They are one-off events that destroy structure to fling some pieces outward. They are not repeatable, controlled, safe, or tunable. You do not get a timetable or a steering wheel, you get, maybe you survive being flung. That matters because it tells you something about the kind of energies and forces involved in actually leaving a galaxy. The only proven exits nature uses are disasters. If you want to replicate that level of effect in a controlled way, You are trying to tame the same mechanisms that throw stars and black holes around, without triggering the destruction. That is so far beyond our engineering that it might as well be magic. So when someone says, well, stars can leave galaxies, so why can't we? The honest answer is, they can, but look at how they do it. They get kicked by black holes, yanked by mergers, torn out by tidal forces. These are not transportation systems, they are collateral damage from bigger gravitational battles. The universe has shown you exits from galaxies, but every one of them looks like a natural catastrophe, not a blueprint for a starship network. And that brings you right up to the edge of the last refuge people usually run to when they hit all these walls. The idea of cheating with new physics. If rockets are too weak, if stars and black holes are too dangerous, if expansion and dark matter and time all block you, maybe the answer is to bend space itself, to open shortcuts, to use warp drives or wormholes and just step around the normal rules. The problem is, when you look at what actual physics says about those ideas, you find a different kind of wall, one made of exotic energy and requirements that make even galaxy-scale rocket projects look reasonable. So the final step is simple. If every normal path out of the Milky Way is either impossible or catastrophic, can speculative tricks like warp bubbles and wormholes really save the dream, or do they just add one more layer to the same you're not leaving message? So after all this, the obvious thought is, why not just cheat, stop playing the slow game and bend space itself? If rockets, stars and slingshots all hit walls, maybe the answer is warp drives and wormholes, the stuff you see in sci-fi where ships jump around the galaxy in minutes. The most famous version of this is the Alcubierre warp idea. The trick there is very specific. You do not try to push a ship through space faster than light. Instead, you imagine a bubble of space-time. Space in front of the bubble gets compressed, space behind it gets stretched, and the bubble itself moves relative to distant objects faster than light would in normal flat space. Inside the bubble, locally, you never break the speed of light. Light still outruns you over short distances. From your point of view on the ship, you're just sitting still while the universe moves around you. On paper, in general relativity, you can write down a metric, a mathematical description of space-time, that behaves like this. That is why the idea went viral. It is not pure hand-waving. It falls out of the same equations we use for black holes and gravitational waves. It looks like a loophole, a way to have faster than light travel without directly breaking the hard C limit for anything with mass. But then you look at what kind of matter and energy you need to make that warp bubble, and you hit a wall even harder than the rocket equation. The bubble needs regions of space with negative energy density. Not just very low energy, actually negative compared to empty space. Normal matter and normal fields do not do that. They have positive energy. Gravity from normal matter curves space in one general direction. To make the warp bubble, you need the opposite sign in some regions, exotic matter that pushes space the wrong way. Traversable wormholes, the other big sci-fi shortcut, have the same problem. A wormhole is a hypothetical tunnel connecting two distant points in space-time. In principle, you could enter one end near the Milky Way and exit the other end in a distant region, skipping the space in between. But the solutions in general relativity that keep those wormholes open and stable also demand negative energy density in the throat of the tunnel. Without it, the tunnel pinches off or collapses. Now, quantum field theory does show that negative energy can exist in very tiny, very local ways. The Casimir effect, for example, involves two plates placed very close together, and the quantum fields between them behave a bit like they have less energy than the space outside. That is a hint that the concept of negative energy is not completely forbidden, but the amounts are tiny and very fragile. We are talking about microscopic effects over tiny gaps, not macroscopic blocks of exotic matter you can shape into a warp ring. To build an Alcubierre bubble big enough for a ship or a wormhole mouth big enough for a starship to pass through, you would need vast amounts of this negative energy. Not a big battery, but something on the scale of planets or stars in mass energy, and with the opposite sign. Early estimates for warp drives literally came out with numbers comparable to the energy content of entire planets, even galaxies. Later refinements and clever tweaks in the math have reduced those requirements a bit, from universe-level ridiculous to still completely ridiculous by any engineering standard. Even in the more optimistic versions, you're still looking at something like convert a significant fraction of a star's total mass energy into a very precise configuration of exotic fields arranged just right around your ship and control it perfectly without it blowing up, collapsing, or producing deadly side effects. That is not just a step beyond our technology, it is a step beyond anything we can currently design even in principle. We do not have a working theory of how to produce and arrange that much negative energy, we only know the equations would like to have it. There is another layer too. If you allow stable warp bubbles and traversable wormholes freely, you have to worry about causality, about cause and effect. Many of these solutions let you arrange paths where you can effectively send signals into your own past, or create time loops. That leads to paradoxes unless something else in the physics stops it. A lot of researchers take that as a hint that, in a full theory of quantum gravity, the universe probably forbids these macro-scale shortcuts in practice, even if we can write them down in simplified models. And then comes the observational side. If the universe were full of usable wormholes or large warp-like distortions, they would leave signatures. They would bend light in strange ways, distort the cosmic microwave background, change how galaxies lens each other, or mess with the large-scale structure in ways our surveys would pick up. We map the sky in radio, microwave, optical, X-ray, gamma ray. We map the tiny ripples in the cosmic microwave background. We measure gravitational lensing by galaxies and clusters. All of that data fits a picture of a universe that is mostly smooth on large scales, with gravity behaving as expected, and no obvious network of shortcut tunnels. If traversable wormholes are out there, they are either extremely rare, extremely small, extremely short-lived, or hidden in ways that make them useless for practical travel. If huge warp-like distortions exist, they are not common enough or strong enough for us to have noticed them in all the precision cosmology we have done so far. Space-time, as far as our best measurements can tell, is not full of open doors, is just curved in the normal way by matter and dark energy. So where does that leave you? Every time you try to dodge the normal constraints, rocket fuel, energy costs, radiation, dark matter, expansion, by appealing to exotic new physics, the bill comes back higher. Warp drives and the wormholes are not free upgrades. They demand forms of matter and energy we have never seen in usable amounts, levels of control that make even Dyson swarms look simple. And they would probably leave strong fingerprints in the universe if they were common. We do not see those fingerprints. Put all of the pieces together now. The rocket equation punishes high speeds. The speed of light is a hard limit, not a suggestion. The interstellar medium turns into shrapnel when you go fast. The galaxy's gravity and dark matter halo set escape speeds that only catastrophic events ever reach. The local group binds you even if you beat the Milky Way. Biology is too short-lived for the timescales. Communication fails across galactic distances. Civilizations drift, decay, and forget long before million-year projects finish. The universe's expansion is slowly cutting off everything beyond your local island, and the exotic cheat codes, warp, bubbles, and wormholes sit behind theoretical and energy walls that make them look more like mathematical curiosities than engineering plans. So in the end, the message is not, you're absolutely magically forbidden from ever leaving the Milky Way. Physics rarely gives you a simple no. Instead, it stacks every difficulty you can imagine on top of each other. For any civilization remotely like us, made of normal matter, bound by biology, limited by real engines and real social systems, the Milky Way is not something you pack up and depart. It is the stage you are born on, the arena you operate in, the environment you might explore more deeply if you become extremely advanced. But in all realistic futures, you do not step outside this galaxy and watch it fade behind you. You live, evolve, and end inside it, along with every other civilization that ever appears here. until the stars themselves run out of fuel and the lights slowly go dark. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.